So as we start Module 3 here, we're going to break this down into two different sections. We have Module 3.1 and Module 3.2. In Module 3.1, this right here, what we're going to do is we're going to be going through all the theory and equation from the beginning part of Chapter 2 in our textbook, and this relates back to sections 1 through 4 in our textbook. Now within this here, what we'll do is we'll go through all the different theory and key equations for the conduction heat rate equation, thermal properties of matter, thermal conductivity, a couple other relevant properties, get into our heat diffusion equation, and discuss boundary and initial conditions. And then we'll take this information that we learned in Module 3.1 and we'll apply it to some example problems that we're going to work on in Module 3.2. So as we get into Module 3, this is going to cover Chapter 2, the beginning part of Chapter 2 of our textbook, where we focus on Fourier's law and the heat equation. So here is Module 3.1. So again, introduction to conduction. We talk about Fourier's law, heat equation, boundary and initial conditions, thermal physical properties, and typical methodology for a conduction analysis. So the first thing that we want to discuss here is Fourier's law. Well, what is Fourier's law? Well, this is a rate equation that allows the determination of the conductive heat flux from the knowledge of temperature distribution in a medium. So there's a couple different things that we should note here that I've highlighted in yellow. We are dealing with our heat flux again, so everything we've learned about heat flux is going to come back again from Chapter 1. And we're also talking about a temperature distribution. Now we've learned a little bit about that and what we're dealing with for different temperatures. We're also talking about in different mediums. How is this going to play out with different mediums that we're going to be dealing with in these problems? So what does this look like in general form? Well, in our general vector form for multi-dimensional conduction, we have this relationship here, that our heat flux is equal to our negative K times our gradient of T, where again, K is going to be our thermal conductivity and T is our temperature right here. So a couple implications that we want to take a look at for one of these equations. Heat transfer is in the direction of decreasing temperature. So what does that mean? It goes from hot to cold in decreasing temperature. This is the basis for the minus sign. Now what Fourier's law also does is this serves to define thermal conductivity. So if we rearrange this equation here, we can solve for K, our thermal conductivity, and this is equal to our negative heat flux divided by our gradient of our temperature distribution right here. Another thing that we want to note here is that this direction of heat transfer is going to be perpendicular to the lines of constant temperature, or what we've called our isotherms. So we can see that up here in this diagram here. We have right here, here's our isotherm right there, and we can see right here our direction of heat transfer is going to be perpendicular right there to that isotherm. So at any point as this moves along, it's going to stay perpendicular to that isotherm. Another thing to note is take a look down here. As with any problem that we do, we're going to want to establish a standard coordinate system here. So right here, I just have the standard x, y positive going up, x positive going to the right. So if we think about this being perpendicular to the isotherm, in this particular case right here, it's going to have both an x and a y component. So we're going to do out a little bit of trig as we go through this in order to break it down and solve this type of problem in terms of its x and its y components. And that's exactly what we're talking about here when this heat flux vector right here, as we can see right there, our heat flux vector can be resolved into its orthogonal components or its x and its y components. So we briefly discussed breaking this down in terms of its Cartesian coordinate systems, our x and our y. Well, this could also be in 3 dimensions as well. So this is what we'll discuss here, is looking at our components for our heat flux right here. So if we're talking about our Cartesian coordinates here, this is temperature, and again, our coordinates are x, y, and z if we're dealing with our Cartesian coordinate system, and we'd have to choose what is our x, y, and z coordinate system here. So we draw something like this here, where we'd have potentially our x going over here, our y coming up here, and we'll have our z coming out of the slide here. So that would be our standard Cartesian coordinate system there. And this relates back to equation 2.3 in our textbook here. And we can break this down in terms of our heat flux in our x direction, heat flux in our y direction, heat flux in our z direction. And we have that governing equation that we saw there, where this is going to be equal to, for our I hat, or our unit vector in our x direction here, of negative k times our delta t over delta x, our partial of temperature with respect to x right there. And then for our y direction here, we can see it's negative k. In our j hat direction here, times now our delta t over delta y there for the partial of temperature with respect to y. And then in our z direction here, our k hat unit vector over here, it's negative k times our delta t delta z, our partial of a temperature with respect to z. And again, this relates back to equation 2.3 in our textbook. Now, we could potentially be doing this in a cylindrical coordinate system. So this is where you want to look at the problem, understand what's going on, and try to determine what is the best coordinate system we want to use. Are we dealing with things rotating in terms of angles? Are we dealing with things in planes? All that will help you make a decision. This is stuff that we've seen before in previous courses, your statics, your dynamics courses. All of those, we've had to make this decision before. So these same things apply when we're dealing with our heat transfer course. So if we're talking about our cylindrical coordinates, this is temperature dependent upon R, phi, and our z right here. So we can take a look over here. Well, z is our direction here. If we wrote this back to a standard x, y, z Cartesian coordinate system here, r is your distance coming out from that central z-axis, and phi is the angle that we're rotating about right here from that z-axis in our xy plane over here. So it still defines whether we give it an x, y, and a z, or an r, phi, and z, it still defines that point, that location of that object or point of interest right there. So we break this down with cylindrical coordinates for our heat flux here in terms of our r. So our heat flux in the r direction is the same thing here. We have our negative k, our delta t times, delta t over delta r here, our partial derivative of temperature with respect to our r position right there. We still have our unit vector here of our I hat unit vector. Then for our theta direction, we have negative k times our delta t over r times our delta phi right here in our j hat direction. And then for our z direction for heat flux here with cylindrical coordinates, it's negative k times our delta t over z times our k hat direction right there. So this relates back to equation 2.24 in our textbook for if we're dealing with cylindrical coordinates. So our next coordinate system we're going to talk about here is our spherical coordinate system here, and this is relating temperature to r, phi, and theta. So now rather than dealing with our z direction as we did with cylindricals, we're going to refer to this by an angle as well here. So if we come down again to our standard coordinate system, our x, our y, and our z, how do we relate this to our spherical coordinate system here? Well, we can still see our r's coming out from our origin here, and this comes up that distance there. So there's our r distance to our point of interest there. Whereas now, rather than calling this with z as a height up, this is our angle off of our z-axis right here for our theta, whereas our phi is still our angle here off of our x-axis on our xy plane right here. So now this relates down to breaking this into our heat flux in the r, heat flux in the theta, and heat flux in the phi direction right there, relating back to equation 2.27 in our textbook. Where we break this down for our r direction, we have this relationship right here where we have negative k times our delta t over delta r in our I hat unit vector direction, and our theta direction here, it's negative k times our delta t over delta theta here. And we have an r term down, our radius is down there as r delta theta on the bottom in our j hat direction. And if we're talking about our phi direction here, it's negative k times now our delta t over r sine theta times our delta phi right there in our k hat unit direction right there. Now, something that's important to consider with this here is even if we're dealing with these angular coordinates here, is your phi or your theta in cylindrical or spherical coordinate systems, the temperature gradient is still going to be based on temperature change over a length scale. So when we're talking about our units and doing unit analysis out here, we're still going to be looking at units of degrees Celsius per meter or degrees Fahrenheit per inch or something like that, and not our temperature degrees Celsius per degree or degrees Fahrenheit per degree. We're still dealing with this as a unit length over here. So that's something important to consider, especially when we're doing our unit analysis and conversions. Now, if we're talking about our heat right here, just for a simple case of a one-dimensional radial conduction right here in either a cylinder or a sphere, which is going to be a lot of example problems do similar to this here. Let's just take a look at the cylinder first, simple case here. Well, our Q sub r is going to be equal now to our AR times our heat flux R direction there is equal to 2 pi R times our L times our heat flux in the R direction right there. And all that's doing is saying, okay, we've just converted, this is our area there. So this right here gives us our area term right here. Or if we're dealing with Q prime R, similar down here, we have this A prime R times our heat flux right there in the R direction. We can take this A prime R is now given to us by 2 pi R right here. So you can see one is dependent upon length and one does not. So nothing different there. Same these definitions from the beginning of the semester. Then the same thing if we're dealing with a sphere here, our Q sub R is equal now to AR times our Q prime, where our area here now is the area for a sphere here. So our typical equation for area of a sphere is 4 pi R squared. So that's where that term comes in here when we're talking about our heat rates for these cylinders and spheres. So now let's take a little bit more detailed look at our heat equation here. So the heat equation is a differential equation whose solution provides the temperature distribution in a stationary medium. Now this is based on applying the conservation of energy, which we've seen before, to a differential control volume through which energy transfer is exclusively by conduction right now. So if we take a look at this in terms of Cartesian coordinates, we have this diagram here. Well, we can see we have this temperature element on the inside here based upon x, y, and z, or our Cartesian coordinates right here. We can zoom in on that here, draw our Cartesian coordinate system right here. So now we're saying x positive to the right, z positive going up, y positive going back there. So again, we do our right-hand rule with this. We put our fingers along our x-axis, curl our fingers towards our y-axis. We can see that z is positive coming up here. This is just something I want to give you a refresher on. That right-hand rule is definitely going to be your friend, especially as you're tweaking and moving this coordinate system for different types of problems. Always good to double check and make sure your sign convention is correct. So as we take a look at this diagram here, we zoom in on the element right here. So there's your dx, your dy, and your dz relating back to your Cartesian coordinates right there for the differential sizes of this element piece right there. We can see all of our heat rates in the x, y, and z direction coming in and out of this here, and our stored energy terms inside the cube there. So now, from all this information, we now have this governing equation, which we can relate back to equation 2.19 in our textbook. You see this first term here. Now, what this term here is this is the net transfer of all thermal energy into the control volume. So our inflow and our outflow right there, because this is the net transfer right here. Then we have our Q dot term, or our thermal energy generation term right there. And this is equal to, over here, our change in our thermal energy storage over here. So this should look familiar right here. These are all our terms again, x, y, and z for our Cartesian coordinate system. So again, this relates back to our governing equation shown on page equation 219 in our textbook. So next, let's take a look at our heat equation in our radial systems here. So the first system we're going to look at in a radial system is our cylindrical coordinate systems here. So this again deals with our r, z, and phi coordinates for this here for when we're dealing with cylindrical. So as we take a look at this differential element in here, bring it out, we can zoom in on it here, and what we can see is we have our dr direction right there as it comes out in the radial direction by r right there, and then we can see our dz direction going up right there, and then we have our phi direction as well right here, r d phi direction right here as we come along that there. And we can see our heat rates around our differential element here. Now this relates back to equation 2.26 in our textbook here, where we have this general definition for our heat equation for cylindrical coordinate systems. We have 1 over that radius r over delta d dr right here times our k times our r value there binds delta t dr right there, plus we have now 1 over r squared times dd theta or phi right here, times our k times dt d phi here, plus now in our z direction here, we have d dz times our k times delta temperature with respect to z down here, delta t, delta z there, plus our q dot term, and this is equal to our right-hand side of the equation, our rho c sub p times our delta t over delta t, our partial differential temperature with respect to time right there. And again, this relates back to equation 2.26. So again, we break this down. There's your r components right there. There's your phi components here, and there's your z components there relating to our cylindrical coordinate system from our general governing equation from equation 2.26 for our heat equation for cylindrical coordinates. Now we can do the same thing here and take a look at this for our spherical coordinates as well. And again, now if we're dealing with our spherical coordinate systems here, we have our radius term, we have our phi terms, but now instead of z, we have this theta term up here. So we can come down here, here's our dr term, and we're looking at our element right there. We go up top here, here's still our r sine theta d phi term right here as we're going with our phi direction right there. And now we can see this other direction here is our r d theta term right here rather than our z term right there, dealing with this in spherical coordinates here. And from this we can come up with our general heat equation for spherical coordinate system, which relates back to the equation 2.29 in our textbook. So we have this 1 over r squared delta dr, or delta r right here, times now our kr squared times our delta t over delta r there, plus, now if we're dealing now with our phi term of this right here, or 1 over r squared sine squared of theta times our delta over delta phi right here times the same now k delta t over delta theta, our partial of temperature with respect to our phi term right here, phi not theta, plus now we have for our last term, for our theta term over here, we have 1 over our r squared times the sine of theta times our d theta there, times now our k times the sine of theta over dt d theta, delta t, delta theta there, plus we still have our q dot term there, and on the right-hand side of the equation, we have that rho Cp times, in this case here, our delta t over delta t there, or our partial of temperature with respect to time right there. Again, this relates back to 2.29 in our textbook for our heat equation for spherical coordinates. So let's take a look now at this heat equation for a special case here. Now the special case we're going to look at here is a one-dimensional conduction in a planar medium with constant properties and no generation. What I want to stop to mention here is these are important phrases you're going to see in a lot of the problem statements for example problems you're working through in the book and for some of the homework problems and exam problems you have throughout the semester. Now with this one here, what we want to do is really pay attention here. So it's a one-dimensional conduction, planar medium, constant properties, no generation. So what simplifies down? This is going to help us determine which equations, what governing equations we're going to use and what we can do to simplify down the solution to our problem. So what this does here is we have our partial with respect to x of our k of our partial temperature with respect to x right here is equal to our rho Cp of our partial of temperature with respect to time down here. So we can go through and this can become, when we do out a little bit of our math right here, we end up with delta squared t over delta x squared now right here, or our second partial of temperature with respect to our x direction here. And this is equal to, on our right-hand side, if we do this out, our rho times our Cp, all that here, we can reduce this down from some of the governing equations we've seen earlier. This becomes 1 over alpha times this delta t partial of temperature with respect to time. Now, where does alpha come from? Well, this is our thermal diffusivity of the medium right here, where this is equal to our k over our rho Cp right there. In this case here, our units for this would be in meters squared per second. So this is important now. We want to do our unit analysis, especially if we do some of these simplifications for these special cases. We really want to make sure that our units in the end are what we'd expect them to be for whatever it is we're solving for. So next I want to discuss our boundary and initial conditions here. Let's take a look at a simple case here. We're dealing with transient conduction. So this is heat transfer in the first order in time requiring a specification of this initial temperature distribution right here. So because we're just dealing with first order in time right here, this is what we need for our initial condition here is initial temperature distribution. So we talk about temperature right here, distribution in our x direction relative to time right here. Well, initially our time is going to be at 0, so t becomes 0 there. So we have temperature in our x direction, wherever x may be, as it varies in our x direction, at time 0 right here. Now, since our heat equation is second order in space, two boundary conditions, because we're dealing with second order here, there's going to be two boundary conditions must be specified. Now, there's a couple different common cases that we can take a look at below here. So the first one, let's take a look at the simple case of a constant surface temperature right here. So this is the case as in many problems that we're going to go through and solve. We can see on this left side over here, we have some wall, some surface over here, where we have the temperature of that surface denoted as T sub S. Now if we go away from that wall a certain distance right here, we can see what happens to our temperature as we're moving away from the wall. So we can see over here as we move away from the wall, our temperature goes like this right here. And as we keep going out here in distance, a certain time is going to be equated with that distance away from the wall. Now, if we think about this in terms of our governing equation right here, where we have temperature of x comma t right here, if we're talking about at the surface, right at this surface here, well, according to our coordinate system right here, x is 0. So our temperature right at this surface here, no matter how long we stay there, is going to be our T sub S, our surface temperature, because we're a distance of 0 in the x direction away from that wall. And this is the case for a constant surface temperature. So now we're going to move on to another common case right here. For this common case, we're going to take a look at the constant heat flux right here for applied flux and for an insulated surface right here. So let's take a look at the first case over here. We're dealing with an applied flux. So we can see right here, here's our heat flux right here at the surface right here applied directly to this surface here. We can see as we go out some distance x right here from the surface, our temperature distribution follows this red curve right here, where this is temperature relative to our position and time right there as we move out there. And if we recall back for our general vector form for our heat flux right here for multi-dimensional convection, we had that our heat flux was equal to our negative K delta T. So we have this relationship down here for our applied flux right here at this surface right here. So when x is equal to 0, which means we're right at the surface here where the heat flux is applied, we have our our heat flux there is equal to our negative K with our delta T delta X right there. We'll plug in that delta X equals 0, and that just is our heat flux right there at our surface. Now, if we move on to an insulated surface and we think about this over here, we're going to have this surface right here, which is going to be insulated. So if we take a look at our general governing equation here, when we're right at this insulated surface, when our x right here is equal to 0, then our dt dx is going to be equal to 0 right there for this special case of an insulated surface as we're dealing with this constant heat flux. So next we're going to move on to our last common case we're going to look at here, and that is for convection right here. Now if we see down below here, we have this diagram here. We can see there's our surface again right there. Our distance going away from the surface is our x direction here. And now we can see we have convection occurring over here. We have the temperature of our gas right here, and we have our H value here, or our convection heat transfer coefficient right here. And we can see now we have our temperature when our distance is x at some time right here, right on the surface of the wall here. And as this moves out some distance x away from the wall, we can see our temperature follows this relationship down here shown in the red curve there. Now we have our general governing equation for our convection case here, where we have this relationship here, where we have our negative K, or our thermal conductivity here, times our delta T delta X, or our gradient, or our delta temperature, change in temperature with respect to our distance x right here. When x is equal to 0 right here, this is equal to H, our convection heat transfer coefficient, times T sub infinity, so our temperature right here, or surrounding gas, minus the temperature at the surface right here, T sub 0 at some time. So this is our general governing equation here when we're dealing with a special case of convection. Now I want to move on and discuss our thermal-physical properties here. So within our thermal-physical properties, we're going to define a couple different things. We're going to define thermal conductivity and thermal diffusivity. So when we're talking about thermal conductivity, this is a measure of the material's ability to transfer thermal energy by conduction right here. Whereas if we're discussing the thermal diffusivity here, this is a measure of the material's ability to respond to changes in its thermal environment right here. Now, if we're talking about thermal conductivity right here, we're dealing with units of watts per meter times Kelvin right here. And we see we start over here at 0, and we have the scale right here is 0.1, 0.01, 0.1. We have a log scale, 1, 10, 100, 1000 over here as we're moving across right there. And now what we can see here is we have these different materials that we'll be dealing with right here. So are we dealing with gases? Are we dealing with liquids? Are we dealing with insulation systems, non-metallic solids, alloys, and pure metals? And the thermal conductivity, as you can see, as we go to our higher thermal conductivity, obviously we're getting up close to some of these silvers and metals, things like that. And again, this is the material's ability to transfer thermal energy by conduction. So think about that. That makes more sense. You can transfer it more by conduction right here if we're talking about some of these metals up here. And then you can see, obviously, we don't want a lot to be transferred through when we're dealing with these insulation systems. So our thermal conductivity down here is a little bit lower. And then we can go, if we're talking about our thermal diffusivity here, to the tables back in our textbook. They have a separate one for solids, gases, and liquids. If we're dealing with solids, these are tables A1 through A3. If we're dealing with gases, this is table A4. And if we're dealing with liquids, this is tables A5 through A7 in the appendice of our book. So I'll show briefly these couple of tables so you can see what to look like and what properties you can get from these tables here. So if we talk about this table A1 right here, these are the thermophysical properties of selected metallic solids. This is going to be important. Make sure you understand what material, what medium you're dealing with when you go back to look up these properties in the chart. Now this is things that sometimes in the more straightforward problems, they're going to tell you your density, your specific heat, your thermal conductivity, all that type of stuff right within the problem statement. Well, in more complicated problems, they might just give you a temperature or they might just tell you the name of a material, and you're going to be expected to know that you need to go to the back of the appendice, or if in a job or a group project or a research project in the future, you're going to need to know where to go and find these tables in general to look them up to get all the properties of that material. It's not always going to be given to you in the problem statement. They might just say steel at this temperature. And you're going to have to go ahead and say, okay, now I need to know where to go to look these properties up. So this one here, if we're dealing with a metallic solid right here, for the thermal physical properties of this right here, we can look up all of those right here. Let's just say we were dealing with pure aluminum right here at the top. Well, we see our melting point is given to us here, our density we have there, specific heat, our thermal conductivity. And then the thing to note here is double check your units right here. Kelvin, kilograms per meter cube. And we can see over here when we get to our alpha term here, this is times 10 to the 6. So really look at the top of this table here. Don't just look at the units, but this is this value times 10 to the 6. So make sure you take that into account when you plug it into your problem. That'll happen a couple times through the semester as we're going through and solving some of these sample problems and homework problems. So really do pay attention to what the value is, the units, and if there are any other types of things associated with those values right there within these tables that you're going to plug in for. So this right here, these were your properties at 300 K, while the properties at various temperatures right here, you can see going up here, here's your K and your C sub P right there, and these are for these different properties, different temperatures right here as we go on up for each of these types of materials. So this is just a small section of table A1. Move on to table A2, same type of thing here, but this is for non-metallic solids right here. So again, if we're looking at boron, there's your melting point, your density, so on and so forth as we go across there. Very similar to A1, but now for non-metallic solids there. Then we move on to your table A3, and this is your thermophysical properties for common materials right here. So structural building materials right here, which is something that is going to be curious. You're not always going to be building something out of pure metal right here. You might have some types of binding boards. There's all different types of these here. So these are the common ones here that we can look up from these tables. If you don't see it here in these tables, this may be something that you need to contact the manufacturer about and get these information. Get a spec sheet from them that tells you, okay, I really need to know the thermal conductivity of this material right here. Can you please tell me what those are or give me a spec sheet? Then we move on here to table A4, and this is the thermophysical properties of gases, and this is at atmospheric pressure. So if that changes, again, there'll be a different table you need to go to. So pay attention to the titles of everything. Pay attention to the units of everything in this here as you're going through. Move on to A5. This is for saturated fluids. And again, take a look, temperature, density, specific heat, all across there. This one is specifically now for engine oil right here for this here. But again, this is just one small section of table A5. So make sure you're looking up everything that you need, what temperature you're dealing with it at, and what the material is. Then from that, you can back out all these properties right from the charts. The other thing I want to mention with these charts here is you're going to need to interpolate. Let's just say you were at 275 or 276. You're going to need to do the math right here to do the interpolation to get all your values between these two sets of values here by doing your interpolation. So then we move on to A6, and this is for saturated water. So again, pay attention to your temperature and all of your units here as well as you're going through this. And that brings us now to table A7. This is for liquid metals here, and they give a couple different liquid metals. And again, if it's not listed, this is a smaller table here. That's something you need to actually contact the manufacturer to get this information for. So let's continue on here with an overview for conduction analysis here. And we're going to talk now about the typical methodology for a conduction analysis right here. First here, let's consider the possible micro and even nanoscale effects and problems here. So these are these small elements that we discussed earlier, involving very small physical dimensions or potentially very rapid changes in either heat or cooling rates. Now, in order to find and obtain this temperature distribution, we're going to need to solve the appropriate form. We talked about a couple of different forms of the heat equation based upon which properties, which materials, what our problem statement is. Then once we have this temperature distribution, what we can do from there is apply Fourier's law in order to obtain the heat flux at any time, location, and direction of interest. So we talked about that, varying with time, varying with a location, depending on what the direction of interest is for us, or where we physically are on the object. Now the question is, where do we go from here? This is kind of a really condensed chapter here where we're just discussing the theory behind this and some of these governing equations. What we're going to do with this is we're going to continue on as we move through this course and apply this in other chapters. Where are we going to apply this? Well, in chapter 3, the next chapter we get to, we're going to apply this for one-dimensional steady-state conduction. So keep it simple at first, just a 1D problem dealing with steady-state conduction. Start applying some of these. Then we move on to chapter 4, we add another dimension. So we get into two-dimensional, but we still stay in steady-state conduction. And then we go on to chapter 5, we're going to talk about this applied to transient conduction from there.